Okay, hi everyone. Now let's start the session. Sorry for the problem that we initially had with the Zoom. Okay, now let's say, does anyone have any question regarding the last sessions, the previous sessions? No? Okay, let me. So if you have any question, please let me know, and let me share screen. Okay, I think now you can see me. Great. I wanted to tell you a few things before continuing the session. Do you remember this norm, the unit balls? So here we said this is the L1 norm, the unit ball for the L1 norm. This is L2 norm, and this is L infinity norm or Chebyshev norm. Here, inside of it satisfies in each of these balls, it satisfies this condition for that norm, right? And we can and this is for in 2D when D is 2. D can be 3. If D is 3, for example, this for L2 norm, it will be a sphere, a 3D sphere. I mean, a 3D ball. Also, it includes inside of the sphere, and this will be a cube containing it's inside of it, and also this will be a kind of a diamond, and we can increase the dimensionality. And I wanted to show you this. So when we increase P, this will, so here we are increasing P. This is P equals 1, which is L1 norm. So we are increasing P. It becomes, so when we increase P, this will be go toward this direction, and this also. So in other words, when we increase P, we are doing this. Also here, we are increasing P gradually. Right? So P here is 1, here P is infinite, Chebyshev norm. And although we said P is greater than or equal to 1, but if we decrease P, we'll have something like that. So we'll go inside. We'll go inside. So this is P less than 1, and then until P becomes close to 0, P tends to 0, then it will be something like this exactly. So this is for unit balls. I wanted to show you graphically how it changes regarding the P. Also, about the Lipschitz continuity, also wanted to say something, also answer one of you who asked how we should calculate that. So let me bring that first. Oh yes, I think it's here. Sorry. Where was that? Yes, here. So if you consider this equation, this inequality, we can rewrite it in this way. That I'm explaining why it's an upper bound on this slope. Do you remember I said when we were talking about the Lipschitz continuity, we said this is an upper bound on this slope, and that's the reason, because you can rearrange this inequality, and then you will have this. And what is this? This is exactly the slope, right? The absolute value of slope. So its sign is not important here, and that's why L is always positive. And as you can see here, and what is this? This is a slope. This can also be interpreted as the derivative, because derivative of a function is the slope of the tangent function on that. It's there an approximation on the tangent, on the slope of the tangent function on here, right? So when you tend x toward y, this will become this will tend to the derivative. This slope will tend to the derivative, because it will be the slope of this function the tangent of this function at this point when you tend x toward y, or y toward x, doesn't matter. So therefore you can see it as the norm of the or norm or length of the derivative. So you can see it kind of as this. If it is 1D, then it will be the absolute value of derivative. But if it is multidimensional, then it will be the norm of the derivative, or the length of the derivative. Therefore, you can see that L is an upper bound on the norm of the derivative. And for calculating the L, you can calculate the derivative on the whole domain, derivative of function on all of its domain. So the domain of x, you can see what are the feasible regions for x to be. So on every part of the domain, you calculate the derivative, and then you take the norm. Then you can even, if it's, you can plot it, or you can have it as a lookup table, whatever, and then you take the maximum derivative in this domain. You can set L to be greater than or equal to that maximum. So because L is an upper bound on the norm of derivative. And usually, as we want L to be small, because the bigger the L, the harder it is for optimizing. So we usually like smaller L. Therefore, we can calculate L as a maximum of the norm of derivative. So the smallest upper bound is when it is equal, right? The smallest upper bound when it is equal. This is its smallest upper bound. L is greater than or equal to the norm of derivative, but we can take this smallest L, the smallest upper bound. Therefore, you can see this as a formula for calculating L, where x is on the whole domain, right? So this is how we calculate Lipschitz constant. So this L is also called Lipschitz constant. Does it answer your question? Who was asking that? Someone was asking. Does it answer your question? Yeah, okay. Hoping. Any questions so far? Is it clear? Okay, great. So now it is clear. That's great. So let me bring the page where we were continuing. Okay, optimization problems. So consider a function. I think, yeah, you are correct. So optimization problems. Consider a function f from Rd to R, and it maps x to fx. Then the domain, let it be D. So x is a part of D, and x is D-dimensional, right? What is unconstrained optimization? When we don't have any restriction on the x. We already talked about it, so we can move on. What is general optimization problem for constraint? So constraint, when we have constraint, we have some restrictions on x. We can write it in this way, where some functions of x are less than or equal to 0, and some functions of x are equal to 0. For example, we have m1 inequalities and m2 equalities in the constraints, right? So these are the number of constraints, and this is the objective function which we are minimizing. Also, you might be wondering how we should handle greater than or equal to 0 when because in this in here we are saying that all constraints are either less than or equal to 0 or equal to 0. So what if it is greater than or equal to 0, for example, this case? Then by multiplying it by -1, we can convert it to less than or equal to 0. Therefore, greater than or equal to 0 can be converted to less than or equal to 0, and vice versa. If we have less than or equal to 0, we can convert it to greater than or equal to 0 by multiplying the sides by -1, because it will flip the sign of inequality, right? Great. So, and you might be also wondering why I have put 0 always here. What if there is a constant here on the right-hand side of this inequality or this equality? Then it's easy. If, for example, we have this, then we can bring this constant to the left-hand side and consider this as a new function. So it will be gix0. Doesn't matter. The naming of the function doesn't matter for us, right? So we can always bring that to the other side. Or here also, if we have y ix less than greater or equal to 0, then we can bring it here and consider it as a new function. For example, z of x, doesn't matter, right? The naming zi, the naming of the function doesn't matter here. Okay, here we talked about it. Clear? Okay, so some examples are these. For example, here we can convert this to this. We brought 5 to the left-hand side of this inequality. So we have less than or equal to 0. If it's greater than or equal to 0, we can make it less than or equal to 0 by multiplying it by -1. Also, here we brought 6 to the left-hand side, and it became -6. So we can have this in this way. Now, minimization and maximization, I think we already talked about that. So we move on to this point. Okay, what is feasible point or feasible set? So minimizing f of x subject to y I x less than or equal to 0 and h I x equals to 0. So this is what we had. And what is the feasible set? So the point x for this optimization is feasible if it belongs to the domain of the function, because the function might have some domain, right? The domain of the function. Also, it satisfies the inequalities. So as long as it satisfies these restrictions of the optimization, and it also belongs to the domain of the function, then it is feasible. What do I mean by domain? For example, for log, assume f was log, right? Can x be less than or equal to 0? No. For domain, and what is d here? D means that x is great. So, or we can write it in this way. X is greater than 0. It can't be 0 itself. Sorry, this is infinity. All right. So it means that it's greater than 0. Let me clean it. So it means that this is not 0 including, and it can go to infinity. It can be negative or 0. So this is an example, and these are some restrictions. For example, assume they have a 2D problem. So you have two variables, and you're looking from above. So when you're looking from above, the height is representing the cost, for example. And these lines, as I already had talked about it, so each line shows that on each line the value of the objective function is the same, right? And it means that either it's coming up as a ball or it's going down. We can't see it, but we can say we can have a color legend on this plot saying that it's going up or going down. Doesn't matter. It's either a ball going up or a ball going down. If it's a ball going up, then we want to minimize it, find its minimum. If it's a ball, a reverse ball going down, we want to maximize it, right? So we can have a feasible set like this. For example, this feasible set is some restriction defined by these inequalities. For example, this inequality, we have M1 inequalities, right? Assume this is one of the inequalities, which says that I want it to be here always. There is another inequality which says I want to be here. There is another inequality, assume. linear inequality. It can be nonlinear inequality too, but here in this example we have linear inequality because these are linear lines. So we can have another inequality saying I want to be here, another inequality saying I want to be here. What is the intersection of these inequalities? This region, right? This region. And this region is the feasible set because it satisfies all of these inequalities. And if, for example, there was a linear equality which says that I want to be on this line, and then the feasible set would be only here, which is the intersection of this equality and these inequalities. So this feasible set should satisfy all of these inequalities, intersection of these inequalities, as well as being in the domain of the function. So far clear? And what does it mean? When we want to find the solution of the optimization, we have to be in the feasible set. So the point has to be feasible. If we find a solution which says it is here, we say, okay, the function is maximized or minimized here. It doesn't. We don't care about this because it's not satisfying our restrictions, our constraints. We have to satisfy the constraint, find a solution which is the best, which is minimizing or maximizing functions conditioned on satisfying the all of the constraints, and be in the domain. For example, if you say, okay, the minimum of the log function is -1, the argument of the log function is -1, it doesn't make sense mathematically because x can't be negative for log, right? So it should satisfy all of these. This is feasibility. Now, let's go to the, okay, here. So the constraint optimization can also be written in this way. So if we integrate all of the constraints in the set S, so do you remember? X should be D, X should satisfy inequalities, either both less than or equal to or greater than or equal to, and X should satisfy all equalities, equality constraints. All of these, if we integrate them into the set S, and we denote it as S, we can write it in this way, right? So S can be a feasibility set, the constraint set, so, or feasible set of constraints. And for another example here, as you see, the feasible set is nonlinear. It means that our constraints, our inequality constraints and equality constraints, they were nonlinear. For example, an example for you to understand is that, for example, our objective function is going like this, but my constraint says this. So this is x1, this is x2. And what is this? The constraint is x2 squared is greater than or equal to 0, right? So this is the curve. Sorry, x1 squared, I guess. Something like that. But yeah, we can also have, I think, a better thing that I can come up very fast. I need to think about this part, but a better constraint that I can think of very fast about it is this. What is this? This is x1 squared plus x2 squared. This is a radius, right? And what is this? For example, we want to be, the feasible set is here. It means that x1 squared plus x2 squared should be greater than or equal to 1. For example, this is 1, the radius 1. So this is the constraint, and the feasible set is nonlinear, as you see, nonlinear. It means that the constraint is nonlinear because we have a squared here. If we have linear constraints, then the constraint would be like this, because each of these will be a line. A line. It's so obvious that the constraints here are linear, or line or hyperplane, right? I'm drawing in 2D, but if we draw it in multidimensional, each of these will be a plane or hyperplane. So in 3D it will be a plane, in 4D, 5D 5-dimensional, 6-dimensional, we don't call them plane anymore. We call them hyperplane. They are linear, okay? But here, for example, in 2D, if we have two variables, it's a circle out of a circle. If we have 3D, it will be out of a sphere, a 3D sphere, out of it. If it is 4D, 5D, 6D, multi-dimensional, we'll call it a hypersphere. It will be out of a hypersphere. So when we say hyper, it means that we are usually in higher dimensions. Hyperline is the same as hyperplane, hyperplane, hypersphere, hypercube, and all of these things. So now, so what is convex optimization problem? So far, if you remember, we talked about convex set before. We talked about convex function, but this is the first time we are talking about convex optimization. So this is the third convexity concept that we are dealing with. We are introducing it right now. Whenever we have an optimization problem where the functions f and y, so this function, the objective function, and the function of the inequalities, okay, are all convex functions. So we already introduced the convex functions. And now, as long as the objective function and the inequality constraints, they're functions, because this can be a function, right? Like this. This is a function of x, like this, for example, an example. This means example, right? So if all of these are convex functions and the equality constraints are affine functions. What is affine? You can see affine as linear. So this is a linear function. Like, for example, f of x equals x is a linear function, or f of x equals alpha x, where alpha is the slope of this line, is a linear function. Also, now consider this function where we don't pass through the origin, right? Here we pass through the origin, but when we don't pass through the origin, we call it alpha x plus some value, some constant like beta. Okay. Usually we can, in the literature, we call both of these, this and this, linear. But if we want to be more precise, we call it we call this linear when it passes through the origin. But when it doesn't pass through origin, it has some bias. We usually call it affine. So affine is linear, but when we have bias, affine is more general than linear, right? So that's why here, if we had only ax equals 0, then it would be linear. But when we have b, some bias of some constant here, then this equality, because you can write it also in this way, right? Ax minus b equals 0. So we have some bias. So this is an affine function. This is also called a linear function. Doesn't matter. They are usually used interchangeably. But when we say affine, you usually mean that there is some bias too. There might be some bias. The bias might be 0. So when we have this format of the optimization problem, the objective function, and the inequality functions are all convex functions, and the equality constraint is an affine constraint, then this is called a convex optimization problem. Okay, and usually the easiest problems to deal with in optimization are convex optimization problems. Boyd also says that, this is a quote from Boyd, as long as you can formulate your problem as a convex optimization problem, then you are done. You can absolutely solve it using optimization and find its global minimum or maximum. So see, do you remember we had local minimum, local maximum? We can also have stationary points, saddle points on all of these things. But when we have convex optimization problem, we are sure that the objective function is convex. Also, these constraints are convex, and this is also convex, right? This affine is also convex. So it means that everything is convex. All functions are convex. It means that we are sure that we don't have any saddle point. We are sure that we always have global. All local minimums are global. For example, we are either here in this case, right, or this case. This is a strongly convex, and this is convex, right? This is the strongly convex. In convex function, we might have several local minimums, but all of them have the same value. So we always have the same minimum function value. It means that we always have one global optimum for the function value. We might have several argmeans, but we have one mean, right? Also, if it is strongly convex, it means that we only have one argmean, and that argmean gives us the global minimum too. Therefore, we are satisfied saying that, oh, now it's an easy problem. We can definitely find its global solution. So now let's talk about some of the standard problems, which are all convex problems. So these are different types of convex optimization problems. One of them is linear programming. So when we say programming in optimization, it doesn't mean coding, okay? So programming has different meanings in the literature. When we are talking about coding, like Python coding, Java coding, and these things, programming means coding. We might have in algorithm, also we might have dynamic programming. So we have also programming in algorithm. But dynamic programming is also related to the optimization too. So programming in optimization means optimization. So linear programming means linear optimization. Whenever you in the literature of optimization see program, it means optimization. And linear programming is linear optimization. And what is it? When the objective function and equality constraints are affine functions. So this is affine. This is also affine. And this is an affine inequality. So everything is affine here, as you see. And this is, as you see, is a special case of convex optimization problem. So this is linear programming. And that's an interesting thing. Everything is affine. So here, for example, the cost is like this. So the cost is linear too. See, this is cost, the objective function. The cost is linear. When we were drawing in previous slides, for example, I was drawing like this, cost like this. It was a bowl coming up or going down, doesn't matter, okay? But this is, as you see, completely non-linear. The cost was non-linear. Although the cost was convex here, but the cost is non-linear because you can see it has non-linear lines. But in linear programming, even the cost is linear. So the cost is a plane or hyper. Here it's a plane because you can see the third dimension, the height here as the cost. So it's a plane. If you look at my hand, for example, it's going up or going down. You can have the plane going up like this, going up like this, going up in that direction, going up in that direction, going down, always, but it is a plane or hyperplane. Okay. If we had only one x, if the variable was one dimensional, then the cost would be a line. Okay. Would be affine, a line. It can have bias too. But when we have two dimensions, two variables, the cost would be a plane. When we have three variables as inputs, the cost would be a hyperplane. Although it's linear, but we should imagine it. We can't visualize it, right? So when the cost is linear, and as you see, even the constraints are linear. So here it says that I want to be here. There is another line saying that I want to be here. There is another line saying that I want to be here. There is another line, another constraints I'm talking about here. These, I want to be here. Another constraint saying that I want to be here. We might have a line here. I'm talking about this now. It might be a line passing through this saying that I want to be on this line. Or when I say line, you can see it as in multidimensional as a hyperplane, right? When I say line, I'm talking about 2D. So when we go to multiple dimensions, then this becomes a hyperplane or a plane in multiple dimensions. So when it says, it might be said, I want to be on this line, then the feasible set would be only this here, the intersection of all of these feasibility constraints. So this is what we have. So this is, as you see, linear programming. In this session, we'll go and see how we should solve linear programming problems. And as you see, by the way, the feasible set is a polyhedron. This is a polyhedron, right? This is in mathematics, this is called a polyhedron. You can see it in multiple dimensions too. This is in 2D. In multiple dimensions, when you have some polygon where every edge is a hyperplane, so it's linear. You can see such as a cube, but you might have more number of edges. So in this case, then it's called a polyhedron. Quadratic programming or quadratic optimization is another type of convex optimization problem where the objective function here is quadratic. Do you remember we introduced quadratic form in several slides ago when we said that this, for example, is a quadratic form? We might have more general case where we have a P here, where P is positive definite. It means that, or its second derivative is greater than 0. Okay, and why do we say that? Why do we say that? Because when we want to minimize it, we are talking about minimization, right? This is a quadratic form, right? We want it to be facing up, so we can find its minimum. Therefore, its second derivative should be greater than 0. Why is P second derivative? Let me prove it to you here. So consider this objective function. Let's take the first derivative. First derivative. What is f prime, which is the first derivative? It will be 2px over 2. So this, the derivative of this will be 2px. This will be q, because this is linear. Like when you take the derivative of 3x, it becomes 3, right? And this is a constant, therefore its derivative is 0. Let's take another derivative, so it will be f double prime. Then we'll have p, these twos cancel out, and so we'll have px, so its derivative p transpose x maybe. So its derivative is p, and this q, its derivative is 0. Therefore, the second derivative is p, right? And for minimization, I want the second derivative to be greater than 0 in order to face in for the function, objective function, to face up. Therefore, I can find this. If we were maximizing this function, then p should be less than 0. So the second derivative would be 0. Therefore, it was facing down, so I could maximize it, right? This is one thing that I wanted to talk to you about. Also, it's a symmetric positive definite function. This means this. This means this. And so it's a quadratic, and the constraints are linear. So the constraints are affine, you can say. The constraints are affine. However, the objective function is quadratic. It means when we say quadratic, it means that it's something like a squared, like it has 2 x's, or in 1D it's x squared. All right. So when this is in vector form. So here again, the cost, as you see, when we are talking about a bowl, it's a quadratic form, right? We already talked about it. So the cost is quadratic. However, the feasible set, the constraints are linear. So the feasible set is a polyhedron again, right? Like this. It says I'm here, it says I'm here, it says I'm here, something like that. So we have this is quadratic programming. So far clear, everyone? Can you please give me feedback? Can someone say anything?
Clear.
Clear? Okay, great. So now let's talk about quadratically constrained quadratic programming. Again, programming means optimization here. So what is this? The objective function is quadratic. The inequalities constraints are also quadratic. When we say quadratic, it means that, by the way, it can be affine too, right? If you set m to 0, then it would be affine. So I'm saying that when we say quadratic, affine is a special case of quadratic. Therefore, you can see linear programming as a special case of quadratic programming. It means that if you have an algorithm which can solve quadratic programming, it can definitely solve linear programming too, but not vice versa. When you have a problem just for linear programming, it might not be able to solve quadratic programming. So in this QCQP, the objective function is quadratic. The inequality constraint is all of them are quadratic, and the equality constraint is affine. And as you see, cost here is quadratic. The feasible set is also curvy, quadratic. But when I say curvy, this is not quadratic, right? The quadratic needs to be like a bowl. It doesn't need to be only curvy. Curvy in a way that it's only like a bowl. It's like this, like x squared, right? It can be it can spread or it can be narrow, but it needs to be like a bowl. So this is feasible set, and this is the cost, and both are like a bowl. We can have a line as a fine equality constraint too. What is semi-definite programming? You hear it a lot in the literature of optimization. Semi-definite programming, also short SDP, you can call it. So when you have, what is this? So C is a constant, and you can trace makes it a scalar. We already introduced trace. You can see it as a summation of diagonal, right? And Cx, so by the way, X is a square matrix. It means that it's the number of rows and the number of columns are the same. And here we are saying that it's positive semi-definite, meaning that all of its eigenvalues are greater than or equal to 0. And what is eigenvalues? I already talked about it a bit, but let me briefly tell you. So when you have a function, you can have eigenvalue decomposition. So you can decompose this matrix when you have a matrix. You can decompose this matrix in any way. Different ways there are, like Cholesky decomposition. There are some famous decompositions. One of these decompositions, so when you say decomposition, it means that you can write it in as a multiplication of 2, for example, functions, or 3 functions. Sorry, matrices. You can write a matrix as a multiplication of 2 matrices, 2 other matrices, or 3 other matrices. In other words, you are decomposing X into 3 matrices or 2 matrices. This is called matrix decomposition. And there are several methods for matrix decomposition. One of them is eigenvalue decomposition. And eigenvalue decomposition gives you eigenvectors and eigenvalues, right? So eigenvalue, what are eigenvectors? Eigenvectors show the important directions that the matrix shows. So every matrix shows some important directions in the space. The eigenvectors, you can see them as important directions of that matrix. For example, an example, if the matrix is a covariance matrix, those eigenvectors show the directions where you have most variance, most spread of that matrix. So when you have some data, you form the covariance matrix, you take the eigenvalue decomposition. The eigenvectors are the directions of the spread of the data. For example, these are some data points. If you take the eigenvalue decomposition of the covariance matrix of these data points, these are the eigenvectors. These are the eigenvectors. In machine learning, these are called principal component analysis. Okay, principal component, or PCA. So, and the eigenvalues are the value of the importance of those directions. For example, the eigenvalue of this is more than eigenvalue of this because we have more spread in this direction. So this is the concept of eigenvalue and eigenvector. And this positive semi-definite means that I want all eigenvalues of this matrix X to be greater than or equal to 0. I don't have any negative eigenvalues. And this is a linear function of matrix X. It's like in scalar form, it's like 3x. In matrix form, it's like 3x bold x in vector form. And in matrix form, you write it in this way. 3 trace of x. You can also bring 3 into the trace. So you can write it as trace of 3x. This is exactly this. a linear function of the x. So this is linear, where we have a constraint for saying that it's positive semi-definite, and you have also some linear inequality. This is linear or affine inequalities and affine equalities, right? So affine objective function, affine inequalities, and also what? Another constraint which says that this x is positive semi-definite. When you have this, you can also write it in this way. Two ways to say the same thing. This is also affine equality, affine inequality, and affine objective function, right? All of these, and this is called semi-definite programming. It means that you are optimizing for some matrix where the the feasibility is the positive semi-definite cone. Do you remember we introduced cone to you? And now we have positive semi-definite cone, the cone where all of the eigenvalues are non-negative. And on this feasible set, I'm optimizing some function. So this is what semi-definite programming is. This is just for introduction to you. I don't want you to solve the semi-definite programming, but you will see that we will learn some algorithms which can be used for solving any optimization problem, mostly. So this is what I wanted to tell you. By the way, another thing we should note that so far until this slide, usually in the forms that we were writing for optimization, the objective variable was a vector, right? Or a scalar. Here, the objective variable is a matrix. This is a matrix, right? Now this is a matrix. And as you can see, all of those other forms, that previous forms that I introduced to you, are special cases of semi-definite programming. They're usually can be seen, or they can be converted to, semi-definite programming. So semi-definite programming, that's why it's very important in optimization. It's concept. And as this is what I was saying here. It's a bit slow. I'm on the next slide, but it doesn't go. Just give me a sec. Yeah, okay. So here, semi-definite programming, and as you here, this is semi-definite cone. This is a cone, right? It passes through origin. So the cone, if you remember in previous slides, I said it passes through the origin. So this is the feasible set. The cost is linear. The constraints also are linear. So this is the cost, and this is the constraint, inequality constraints, for example. So also we have a constraint on to be on the or in the semi-definite cone. This is semi-definite programming. Okay, now an important thing is that all standard optimization forms can be restated as a semi-definite programming. So there are special cases of SDP. And interior point method, which we will introduce in the next sessions, or barrier method, they are the two names for the same thing. They can be used for solving various optimization problems such as SDP. Many optimization toolboxes. I don't know if you have heard of CVX or not. CVX is a very important and famous optimization toolbox. It initially came for MATLAB. Later, it came for Python too. It might have in other languages too. So CVX, and it is developed by Stanford people, supervised by Professor Boyd, Stephen Boyd. They use interior point method or barrier method in order to solve that. And usually they can convert their problems into SDP. So that's why it's very important. It's an iterative method. We will see that interior point method that we will introduce later is an iterative point. So it can be time consuming because it's iterative. It doesn't give you the answer in one shot. It needs steps to move toward the solution, optimal solution. And if the optimization problem is a convex optimization problem, it has only one. When I say local optimum, I mean the value. You might have several argmeans, but the objective function value of those argmeans will be the same, and you will have only one minimum for that function, minimum value. which is the global optimum, right? And so these are the important things and some references. Now let's go to linear programming. But before that, do you have any question from these slides? No? Can you please say your feedback? Is everything clear so far?
Yeah, everything's good. Looking forward to diving into
Great.
some questions.
Okay, great. So please participate in the class and have your questions. Even if I don't know any answer, I need to look it up or I need to think about it, I will do it and then I will answer in the next session. For example, you asked me about how to calculate Lipschitz constant. I hesitated about that. I said I need to go and look it up. I looked it up and then I answered you. So always please ask me questions. Thank you. Okay. So you can also ask your question in the chat and I will answer that. So, and this is, by the way, CVX MATLAB software that I said. They have it for Python too. Now let's move on to the, where is that? Yes, linear programming. Okay, there is someone in the chat. It's all clear, thank you. Okay, thank you very much. Great. So now we are in linear programming. So we introduced linear programming. Now we are going to see how to solve it. Again, linear programming means optimization, linear optimization problem, where the objective is linear function in X. The inequality and equality constants are all affine. Affine inequality, again, affine means linear, but we might have bias too. But the bias might be 0, but we might have bias too. Affine inequality constraints and affine equality constraints. All of them in X. When we say affine, we mean in terms of X. We might have some constants too, but in terms of X. For example, if X is a scalar, 3x plus 2 less than or equal to 5, this is an affine inequality in terms of X. But 3x squared plus 2 less than 5 is not affine anymore because you have a squared here, right? And this is, for example, 3x plus 2 equals 5. Right? This is equal. And this is, for example, f of x equals 3x plus 2, for example, right? So standard linear programming standard is usually written like this. So maximize or minimize. You might have maximization or minimization. Again, this is a linear function. Do you know why? Because if you write alpha as alpha 1 until alpha n, and x here, we have it, is x1 until xn. Why do I put transpose here? Because I usually write vectors as column vectors, and for this is a column vector. The row vector transpose is a column vector. So alpha transpose x means alpha 1 x1 plus alpha n xn. It's a linear function in terms of x, right? And this also is a linear or affine inequality. This is affine inequality. So these we have as a standard linear program. But when we say standard, usually in a standard problem, x is all of the variables. So do you remember this? This generalized inequality that we introduced in previous session. And this is a vector. Therefore, it means that all of element-wise, every element is greater than 0, greater than or equal to 0. So it means that x1 is greater than or equal to 0 until xn is greater than or equal to 0, right? And this is a matrix G multiplied by the vector x. This will be a vector, and the vector is less than or equal to h. Generalized inequality means that element-wise. So assume that Gx, we write it by y, whatever. So y1 to yn. So I'm denoting Gx by y, right? And this is less than or equal to h1. So assume h is h1 to hn. This means y1 is less than or equal to h1 until yn is less than or equal to hn. So this is what it means. We can also have, so, but one important thing for a standard problem, either it's maximization or minimization, the variables are greater than or equal to 0. So usually, and you will see even in practical problems, optimization problems, usually it is the case that we have optimization value non-negative. And these are some G is a matrix and H is a vector. And M it shows the number of constraints, right? The number of constraints. If I showed it as N, but it can be M. HM. Because we might have M inequality constraints. Okay, now let's go to the next slide. So equivalently, we have this. We already talked about it, linear inequality constraint 1 until linear inequality constraint M, because we have M inequality. H was an M-dimensional vector, and x1 to xn is greater than or equal to 0. Usually M is greater than or equal to 0. Usually, because when M is less than the number of constraints, we might have some issues. It doesn't matter. I'm saying that it usually happens that we might have both cases where M is less than N or greater than N, but usually we have more number of constraints. And some examples. This is for minimization. This is for maximization. The objective functions are linear, and as you see, we have two inequality, for example, constraints, and also we have this default inequality constraint where the objective variables are greater than or equal to 0, right? So these are some examples. Now some practical examples. I think you will like this part. So practical example 1 for linear programming. And that's, for example, this practical example might be good for management, people in management and these things, or industrial engineering. Industrial engineering, I think you will face this a lot in your job. So a company has 2 products, for example. It can be any number of products. In this example is 2. Let x1 and x2 denote the amount of first and second products to be produced, right? With some scale. Scale might be anything. For example, kilograms or whatever. Or if it's a length-based thing, centimeters or whatever. Therefore, usually x1 and x2 is greater than or equal to 0. Do you remember? I said usually in practical examples, the objective variables are non-negative. Here you can see an example for it. This is the amount of product. It can't be negative. It can be 0, but it can't be negative. That's why in standard problems, usually they assume that the objective variables are non-negative. The company has profits $60 and $30 for the first and second products. So $60 for the first, $30 for the second. So whatever the company produces, $60 profit. Therefore, the total profit is this $60 multiplied by x1 plus $30 multiplied by x2. So for every scale of x1, the profit is $60. For every scale of x2, the profit is $30. Total profit is this, right? In terms of dollars. Now, the resources for these products are limited. So we have the following, we have some restrictions. These are the constraints. We do not want the first product with proportion 8, for example, and the second product with a proportion 3 to spend more than $48, something like that. So 8 times x1 plus 3 times x2, I want it to be less than or equal to 48. I don't want to spend more than $48 for 8 of x1 and 3 of x2. So some kind of restriction. Another restriction might be the other way around. I have the budget to spend at least $25 at least for 4 of x1 and 2 of x2. Therefore, this is a budget that I have. So I can put these 2 restrictions here. I want to maximize this total profit, right? And I know the x1 and x2 are non-negative. So this is we formed this problem, which were in words in English, to a mathematical optimization problem. You can do it in any way, in the other way around too. So you can have an optimization problem and you make a story for it, or you have a story and you make an optimization problem for it. You can do in both ways, right? A practical example too, and this will be interesting for people in physics or in mechanical engineering, I believe. It might be also good for industrial engineers if they work with mechanical engineers. So we can have different practical examples in different fields, right? We can even have it in machine learning, data science, in anything. So I'm just giving you some examples just as a proof of concept. Okay, we have, for example, 2D tanks. It can be 3D tanks too. I will say how it can be converted to 3D tanks. But assume we have 2D tanks like this here in this figure, which are connected from their bottom, tanks of water. So let x1 be the height of water in one of them, like this. This is x1. And let x2 be the height of water in the other one. And let the width of these two tanks for the first one will be 60, and for the second one is a 30. And with some scale, it can be meter or whatever. Therefore, the total amount of water in these tanks will be 60 times x1 plus 30 times x2, right? This is the total water in these two tanks, neglecting the water in here because it's very small. Now, so this is what we have. And assume we want to find a setup where we want to maximize the total water we have in this setup with some restriction. For example, we might have some physical restrictions on water before it comes to the tanks. So the water is coming, right? Water is coming from somewhere to the tank. We might have some physical restrictions, and these physical restrictions might impose these restrictions, linear restrictions, right? If we had nonlinear restrictions, then it wouldn't be a linear programming anymore. But for this to be a linear programming, the restrictions need to be linear. Again, the height of water is always non-negative. It can be 0, but it can't be negative. And we are maximizing this with these two restrictions. And how can it be 3D? If we, for example, we have 60, no, we have 30 by 2 by x. So x the height is the height, 30 is the width 1, and 2 is the width 2, right? So we have width 1, width 2, and the height. It's because it's a cube. So you can consider the multiplication of width 1 and width 2 as the total width. Therefore, you can see this as a 3D tank, where this is a multiplication of the first two widths. Also, this is the multiplication of the first two widths for this tank. So we can see that 3D tanks too. Is that clear so far? So as you see, we can formulate problems or real world problems as linear programming. If the restrictions and the objective function that we are maximizing or minimizing are linear. If they are not linear, they will be general case optimization, which we will go through together in the next sessions, and but not now. Okay. Now let's go to solving linear programming by visualization. When the dimensionality of data, the dimensionality of objective variable, or the number of objective variables, if we consider the objective variables as scalars, the number of objective variables, or if we consider the objective variable as a vector, the dimensionality of this objective variable, if it's either 2, 1, 2, or 3, right? We can solve it using visualization because we can draw it. If it's 1D, I think it's very easy because we only have one x and f is here, right? And if it's 2D, we can write x1 here, x2 here, and see f as the height, the objective function as the height. And if, for example, here for example, and the objective function can be like this, can be drawn like this. And what does it mean? It means that the plane coming up, for example, right? Because the objective function must be linear. And this line means that on this line, the function value, objective function value is the same. Now, if we have 3D, then we can write it in this way, x1, x2, x3, and imagine f as a function in this 3D space. For example, we know that this is the space, and here the temperature is higher than the temperature here. So we know we can imagine f as the value, a function of these 3D space. So we usually when it's 3D, it's harder to visualize, solve using visualization. But in 2D is the easiest, 2D and 1D. An example here, for example, we want to solve this this problem, which is 2D, two objective variables using visualization. And so we draw the first, we draw consider the first constraint. The first constraint, I want to draw it. First, I put x1 to 0, so x1 0. Then we'll have 0 plus 2x2. Consider this inequality as equality for now. Then we will take care of inequality. Then x2 becomes 20. It means that when x1 is 0, x2 is 20. We are here. This is a point. Now, the other way around. Put x to 0, x1 plus 0 becomes equals 40. So x1 is 40. We are here. x2 is 0 and x1 is 40. Now, connect these by a line. Why? Because it's an affine function. So we can connect these two by a line. So this is the equation of this inequality constraint. But when we should see, we are either, when it's inequality, when it's equality, it means that we are on this line. Equality, it means that we are either on this side of the line or the other side of the line. How do we know which one? We can test for a point. For example, 0 and 0, origin. 0 and 0 is not greater than or equal to 40. Therefore, we are on the other way, on the other side of the line. We are on this side, right? I have drawn it here, so I don't need to draw it here again. So now you can do the same for this inequality constraint, and we will get this line. And again, we can put some point in it and see which side of the line we are. We are on this side. When we have equality, it means that we can be on the line too. So either on the line or this side, either on the line or this side. If there was no equality, it means that we are only on that side. And x1 and x2 are greater than or equal to 0. It means that we are only working on the first orthant. This is an orthant where all of the variables are non-negative. So we are working on this orthant. We are not here or here or here, right? Okay. So I should correct this. Sorry, these are not. This shouldn't be in the. I will correct that in the slides. This shouldn't be in the constraint feasible set. So, and this is cost. Cost is coming up. Why? The cost is linear first off, but how do we know whether it's going up, going down? Where is it going up or down? You can see the pattern of this. The more you increase x1 and the more you increase x2, this also increases. It means that it's going up in this way, right? It's going up in this way. And now in the feasible set, where is the feasible set? I have put it here. So this is the feasible, because this is the intersection of these two inequalities. In this intersection, in this feasible set, where is this function, the objective function, minimized? We know that it's been increased by moving toward this direction. Therefore, here we are we have the minimum. But how do we know whether it's here, 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 here? Okay, when we have linear programming, as the objective function is linear and as the constraints are linear, can someone tell me Where should we seek the answer of linear programming whenever the cost is linear and the constraints are linear or affine? Where should we seek the answer? Usually, where does the answer lie? Can someone tell me?
Is it as close as we can get to the origin?
No. Do you know why? Because assume I have this function. Then close to origin, this will be maximized, not minimized, right? So you should see the cost function for that. But I'm saying that whatever the cost function is, assume you have some cost function either going up in this way or in that way. It's linear. It's linear. The constraints are also linear. Inequality constraints linear. Equality constraints are linear. Assume you, for simplicity, assume that you only have inequality constraints. So you have a polyhedron feasible set. You can also imagine it in 2D only. Don't go to 3D or multiple dimensions. Like in this case, you have two variables, and you have a polyhedron feasible set, and your cost is a plane, either going up in this way, doesn't matter. Where in this because you should be in this feasible set, where in this polyhedron, either inside of it or on the boundary of it, should we find the solution? First off, answer this question. Do you think the solution, the minimum or the maximum, is inside the polyhedron feasible set or on the boundary of the polyhedron feasible set?
Well, in this case, is it not where the two equations are equal to each other?
No,
Like
no,
where the two constraints
what I
or
mean, what I mean is this. Assume you have a polyhedron like this, right? And you have some cost which is going up in this way or the other way around, doesn't matter, or in the other direction, doesn't matter. I don't care. Can you imagine and think about it? Do you think the solution will be here or on the boundary? First answer.
It'd be on the boundary.
Yes, on the boundary. Why?
Well, that's the first place the cost is going to hit.
Exactly. The cost will be, so if it's maximization, for example, the cost is going up in this way, right? So the cost will is increasing, and will hit the boundary, because here the cost is less than here, right? So the boundary is where we should seek the solution in. Here, or we are minimizing. Assume we are minimizing the other way around. Here, the value of the objective function is more than here, right? Because again, consider the fact that the cost is linear, so it can't be the way that it can't have this behavior going up and going down again. It's not linear. The cost is always going up or going down. It's linear cost function, right? Therefore, it's either, for example, in this case, minimization, you should seek it here in this boundary. For maximization, we should seek it here. If it was the other way around, it might be like this. This is the polyhedron feasible set, and the cost is like this, increasing in this direction. For maximization, you should seek it here, right? Around here. For minimization, you should seek it around here. Do you agree with me?
Yes. Yeah.
Yes. Why? Again, because the cost is linear. It's not, for example, here, it's not possible for it to go up and again come down. If it was the case, then we might have the solution in the middle of the feasible set. But when it's going always up or goes down, so we should seek the solution on the boundary of the feasible set. So this is one case. Now let's go one step further. Do you think, where on the boundary should we seek the solution?
Well, I guess it's like, oh, go ahead, whoever's speaking.
At vertex.
At vertex, exactly. Exactly. I know that some people said the answer, so it's not just one person. I agree. So at vertex, why do you think it's at vertex? Because for it to understand, you need to only imagine. So assume there is a plane, and you have a polyhedron, and this plane is cutting this polyhedron. So at some point, so the function value is going up. At a vertex, it will leave the, so here, for example, the objective is going up. It's becoming more and more. At here, when it's leaving the polyhedron, it's the maximum. Here, it becomes more than here, but it's not in the feasible set anymore. Here, it's less than here. Here, in this part of the boundary, this is less than this because the cost is going up and up. Here, on this part of the boundary, it's less than here. At a vertex point, if, for example, in a special case, it might involve some rare case where the cost is like this, going up, it's parallel to this, then all of this will be the solution, right? It will have multiple solutions. But again, this part has two vertices in it. So always you should seek the solution at the vertex, even in this rare case. So here, also, if you are minimizing it, here, again, first off, we consensus on the fact that we should seek the solution on the boundary. So you should be either here, where in among all of these, this has the smallest cost, right? Again, here, the cost is in this, the increase in this direction. Therefore, this point is the solution. The cost is increasing this. So for minimization, for maximization is this point. Is it clear to everyone?
Yes.
Yep.
Yeah, great. So these vertices of the polyhedron, again, this polyhedron might be multidimensional, right? We are only visualizing in 2D right now. It might be multidimensional, like a cube or something. The vertices of this feasible set of linear programming are called extreme points. Why? Because these are over the corners. These are extreme points of the feasible set, extreme points, okay? So the solution is one of the extreme points. And that's the beauty. That's the beauty of the linear programming. As the cost is linear, and as the constraints are linear, the feasible set is always a polyhedron, or even a line. If, for example, we have an equality, and assume that the cost might be this, the constraint might be this. So we might have one inequality constraint, another one here, another one here. So 1, 2, 3, 4, 5 inequality constraints, each of which saying that I want it to be here. So I'm here. There might be an equality constraint saying that I want to be on this line. So it's still in the polyhedron, right? But on this line. And again, line in multiple dimensions might be hyperplane. It can be a plane, right? So it might be on a plane, not just a line. Doesn't matter. So as the constraints are affine and the objective function is affine itself, linear itself, then we always should seek solutions at the extreme points, at the corners. Therefore, here we only have one corner and we are minimizing it. The solution is here. If we were maximizing this problem, then its solution would be x1 and x2 equals infinity, and the cost will be infinity because there is no upper bound on this. We can put them infinity because it's going up. But as you are minimizing it, it's here, this extreme point. And you can, for visualization, you can equate this equation to this equation to find the solution of this. How? x1 plus 2x2 minus 40 equals x1 plus x2 minus 30. These will cancel out. x2 equals 10. x2 is equals 10. And if you, again, in this equation, put x1 plus 2x2, and put it back in this equation, 2x2 2 times 10 should equal 40, right? Again, I'm the boundary. I'm talking on the boundary, so therefore I can set it for equal. Then x1 is 20. So x1 a star is 20, x2 a star is 10. I can write it in the vector form. This is a solution, right? So this is the way that we should solve using visualization. We have some other examples, and then we will go to the simplex algorithm. But before that, let's have a break and come back at 8:35. Do you agree?
Sounds good.
Okay, great. Thank you. So see you in 15 minutes. Thank you. Okay, let's resume and let me share screen again. Yes. I hope everyone is back. So now here we have this. Here we have this. So another example for visualization. How can I bring it up? Yeah, okay. Another example is this maxima. Now, previous one I think was minimization, or previous one was minimization. Now this is a maximization problem. So we have these two inequalities. Again, using the same method, you can draw them and see, put a point and see which side of the inequality or the hyperplane we are. Again, we should be greater than or equal to 0. I will correct that part. Here we can't be. Sorry, we need to be in the first orthant. I will correct that in the slides. So we are only here. We are only here in this part, right? Because here, and the x1 and x2 should be greater than or equal to 0. And the cost function is 40 x1 plus 30 x2. Therefore, it's increasing in this way, right? This is cost increasing in this way. Therefore, and it should be on one of these. So this is a vertex. This is an extreme point, right? This is an extreme point. This is an extreme point. This is also an extreme point. We have 4 extreme points here, considering these two. So, and where is it maximized? Of course, here the cost, if you calculate that, will be maximum. You can calculate the cost here too, here and here. So you can, if you're not sure, you can calculate the cost in each of these extreme points and see which one is the maximum, for example, here. And you can intersect these two lines and get this answer. Another example, we might have more number of constraints. For example, here, x1 and x2, this is x1, right? So this is the cost. And this, for this one, where is it? x1 plus 2x2 greater than or equal to 8. So I have showed you here, for example, no, this is for intersection. So first off, let me find this. So if it will be, if we put x1 to 0, then x2 will be 4, x1 to 0. So this is this line, right? And we are on this side of it. For this, it's this line, and we are on this side of it. You can put numbers in it and see, or points in it and see which one is satisfied, so that you can find which side you are in this in the inequality. And you all sorry, x1 and x2 is greater than or equal. This is this line. So where is this line? Let me find the second constraint. So if you put x1 to 0, x2 will be 8. x1 to 0, x2. Oh, this is this line. This line is for the second constraint. We are on this side. So this line first constraint, this line second constraint, this line the third constraint. And the fourth constraint, x1 less than 5, is this. And the fifth constraint is this. And we also have, we are in the first orthant. And as you can see, intersection of all of these is here. So we are, the solution is either, and the cost is linear too. So the solution is either here, 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 or here. We can calculate the cost in these areas and see which one is the solution, right? And for finding these, for example, here you can put x1 to 5 and see, put it in this equation of in this line and see what is it. Also here, here, here. For example, here you can intersect these two lines, like what I have written here in this explanation, and see, you can find out the intersection. So I think it's very straightforward. But before that, you should also note that, for example, here, let me draw it here. So if you are in 1D, if you have only one dimension, now, for example, minimize 3x subject to, minimize is subject to, let me think, 2x less than 5, and x greater than or equal to 0. We might have some other constraints too, but I want to let you know what how it will be for visualization when we only have one dimension. So this means that x is less than 5/2, which is 2.5, and x, so we are on this side, including the line, because we have equal here too. So, and we are in the first orthant. Therefore, we are here, and because x is greater than 0, and 3x is a line which is like this. So if it is 2.5, 3.2.5 is 7.5, I guess. Yes. So it will be this line. This is 3x. And where is the solution? The solution, we want to minimize it or maximize it. Assume if we want to minimize it, the solution would be here. If we want to maximize it, the solution would be this, right? Because f here is increasing in this way, right? This axis is f now. This is the cost function. We can also have in three-dimensional vector, and I mean the three-dimensional objective variable. In that case, these will not be line anymore. These will be planes. Planes. So the constraints will be planes. If it's equality constraints, it will be on the plane. If it's inequality constraints, we will be on either one of the sides of the plane, either this side of the plane or this side of the plane. So we'll have planes, intersection of planes, right? And if we go to higher dimensions, we should imagine it. We can't visualize it easily. So far clear? Now let's go to the simplex method. So as we saw in the pictures, the feasible set determined by the constraints is linear. In linear programming are affine or linear boundaries, right? It's because the constraints are also affine linear. This is the reason. Therefore, the feasible set is like a simplex, or you can see it as a polyhedron. So this is called a simplex or a polyhedron. And I think if, for example, we have 3D, x1, x2, x3, the feasible set will be something like this. So intersection of planes. And for example, all of these constraints are saying that we want to be inside this polyhedron. Something like that, right? Each of them will say, I want to be inside. And so the intersection will be a polyhedron, something like that, where the edges of this polygon are planar, are planes. Therefore, we call it also a simplex. And as we discussed, the solution, because the cost is also linear, some linear cost or objective function. Therefore, the solution, as we discussed, is on one of the vertices or one of the extreme points of this simplex. Therefore, one of these that I'm highlighting is the solution, is the argmin or argmax. So so this point has one x1, x2, x3, right? So this is the argmin or argmax, and the value of the cost function at this point is the mean or max of the function. See, again, these points are. So we start, the simplex algorithm is very interesting. It says that I start from one of these extreme points, and then I move on like this, on one of these extreme points, and I move on the boundaries. For example, here, assume I start from here. I move on the boundaries from one extreme point to another. So from extreme point to extreme point, I move, and I try in this movement, in each movement, I try to improve the cost function. If I want to minimize the cost function, I try to have less value for function, objective function in each movement. If I want to maximize it, by moving from one extreme point to another one, I want to increase the value of the objective function. So I move one by one until I reach an extreme point where I can't move anymore. If I move to one of the neighbor extreme points, the cost function will be worse. For example, if we are maximizing, when we reach the optimal solution, when we move to its neighbor extreme points, the cost will be less when we are maximizing. If we are minimizing, by moving to its neighbor extreme points, we are increasing the objective function. Therefore, then we will be stabilized. We will be stable there, and that will be an optimal solution. This is the simplex algorithm. You can see it's very simple, but it's very interesting idea, and it was a revolutionary or breakthrough in optimization. So it was initially proposed in 1947, and it works on linear boundaries or edges and extreme points of the simplex feasible set. Again, the feasible set, the polyhedron feasible set that we discussed is also called simplex, right? Because simplex, this is also called simplex in topology, right? This is a simplex, like a pyramid, something like that. So you can have a simplex. Obviously, again, the edges are planar. Obviously, the solution is at one of the extreme points. Okay. The simplex algorithm starts from an extreme point and then moves from every extreme point to a neighbor extreme point and improves the cost function. Again, we already talked about it. One of the methods for simplex algorithm is the Tableau method. Tableau method, it comes from table, right? Because we can solve this, the iterations of the simplex algorithm, which we say going from one extreme point to another extreme point, can be implemented by tables, and we'll see. So now let's talk about this. For example, consider this example. First off, when we want to maximize, let's now first focus on maximization, okay, only. Now we have this, so we convert each inequality constraint to equality constraint. Assume that the constraints are less than or equal to 0, less than or equal to something, okay, for now. We convert that as the first step, each equality constraint to equality, each inequality constraint to equality constraint by adding slack variables. What does it mean? For example, consider this inequality. Do you agree with me that the left-hand side should be less than or equal to right-hand side? Therefore, if I add a positive or a non-negative, let's call it non-negative, it can be 0. It might be 0 because we might have equal. So a non-negative variable called a slack variable, then I can replace this inequality by equality, because whatever difference this has from this right hand side, I can put it as for S1. So for example, 30 is less than 50, right? But I can write it 30 plus 20 is equals 50. And this 20 is the slack variable. So I converted inequality to equality, where the slack variable is non-negative because this is less than or equal to. I can convert for each of the constraints, I will add a slack variable, right? And then I convert the inequality to equality constraint. And the slack variables should be non-negative too, because we have less than or equal to negatives. And this positive should be non-negative because it might be 0. The slack variable might be 0. I will fix that in the slides too. So here, that was one step. So this problem that we had inequality constraints is converted to this, right? Here we had the variables are non-negative. We are in the first orthant. We also add these. The slack variables are also non-negative. The objective variables were only 3 before. Now they are 6. Why? Because for each inequality constraint, we added a slack variable. In other words, we increased the number of objective variables from 3 to 6 here, right? For each inequality constraint, we added, which is less than or equal to, we added a slack variable, right? So far clear? Yes?
Yep.
Okay,
Yes.
great. So now here, the cost function, let's call it C. Let's call the cost function C. It means define. This means define here. Let's call it C. And so this is the cost, right? Or the objective function, doesn't matter. And then bring the right-hand side to the left-hand side and equal it to 0. So C minus 6, 1 plus minus 5x2 minus 4x3 equals 0. And so these were the 3 inequality constraints, and this is the objective. Therefore, we have this. So now let's write these. So these were the inequalities, and this was the cost, right? Let's write this as a table. How? In this way. We write the slack variables here. All the objective variables here. The order doesn't matter, but whatever order you choose here, you should stick to it until the end because we'll have multiple steps. You should stick to the order, but the order, you choose some order. The order doesn't matter. And then the cost here, we write it here. By the way, the cost that here we see, and this is minus 6. And when you choose the order, you should take care of, so this is 2x1, right? 1x2 plus here, see, 1x3 plus 1s1 plus 0s2 here plus 0s3 equals, this means right-hand side. Right-hand side. Right-hand side is 240. For again here, a second inequality constraint, you say 1x1. Look at the second. 3x2. Again, if you had changed the order of x2 and x3 here, you should change the order here too. Be careful. So 3x2 plus 2x3 plus 0 s1, we don't have s1 here, plus 1 s2 plus 0 s3 equals 360. Again, do it for the third inequality. For the cost function, minus 6x1, here we have. So minus 5x2 minus 4x3 plus 0 s1, we don't have s1 here, plus 0 s2 plus 0 s3 equals 0, right? So I wrote this as a table. That's why it's called Tableau method, because it's based on table. Now, in maximization problem, choose the most negative value. So here in this row, I mean, in the row of cost, I say in row of cost. In row of cost, choose the most negative value. So here is -6, right? And draw a circle around it. So this is your pivot column. Let's call it pivot column, right? As you see, it's a procedure that I'm explaining to you, and you will see it's very easy, and you will see the reasoning behind this procedure too in a few slides. So this is pivot column, and then we do the mean test. After choosing the pivot column, we do the mean test. And what is mean test? So we divide every value of the right-hand side by every value in the pivot column here. Not here, here. So 240 divided by 2 is 120. 360 divided by 1 is 360. 300 divided by 2 is 150. And take the mean among them. What is this among them? To 120. This is the mean. So we draw a line around it. And this is the pivot row. We call it pivot row, right? The intersection of pivot row and pivot column gives us the pivot value. So far clear? By the way, in the mean test, ignore negative values and 0. So assume you had 0 here. 240 divided by 0 would give infinity. Ignore that. You can write something like this. Ignore it. Ignore that row. If there is a negative value here, or something like that. If there is a negative value here, then, for example, it was -1. 360 divided by -1, ignore it. You would put something like that. So ignore all of those. Among those which you don't ignore, take the minimum. And this will be the pivot row. So pivot column, pivot row. So pivot column, the order is this. Take the pivot column, then do the mean test, then choose the pivot row. The intersection will give you the pivot value. So far clear?
Yeah.
Okay. Great. Now we want to make the pivot value 1, and the other values in the pivot column here in all of these other values in the pivot column 0. We'll see why. We'll see why. So we want for every row, use the row itself. So every row, in order to satisfy this, in order to make the pivot value 1 and the other values in the pivot column 0, we should do what? How should we do that? We should do some calculation in a way that always use so on whatever row you are, always use that row, and the pivot row. So always use that row and the pivot row, and using a linear combination of these two rows, try to make that, if you are in the pivot row, make that 1, otherwise make that 0. For example, here, I want to make here starting from the first row. This is a pivot row, and I want to make this 1. So what should I do? Using R1, the same row, R means row, short for row. So this is R1, this is R2, this is R3, third row, this is R4, right? I mean row 1, row 2, row 3, row 4. And I want, using this R1, the same row that you are in, and the pivot row, again R1. So only have R1 in hand. Using R1, try to make it 1. What should I do? Divide this R1 by 2. 2 divided by 2 equals 1. So this is what I have done. Divide every value of this row by 2. So 2 divided by 2 becomes 1. 1 divided by 2 becomes half. 1 divided by 2 becomes half. 1 divided by 2 becomes half. 0 divided by 2 becomes 0. 0 divided by 2 becomes 0. 240 divided by 2 becomes 120. Right? This is what I'm doing is called, I think, elementary row calculations. As you see, you are by rows, you are doing some calculations in order to make this 1 and the other one 0. So now you have R2. So using the row itself, which is R2, and the pivot row, which is R1, try to make this 0. How? Always put R2, the row itself, so you don't weight the row itself when you are on that. and plus some alpha or 1, try to make it 1. How do I find alpha? You can either do it in your head, or if it is hard for you, you're saying that, okay, I want this 1 or so 1, let me write it here. 1, this value, 1 plus alpha R2 here, which is 2. I want it to become 0, right? This alpha might be positive, negative, or 0, whatever. So 2 alpha equals minus 1. So alpha equals 1 negative half. Therefore, you will have R2, alpha is minus 1 over 2, right? Minus 1 over 2 R1. And put it in R2 again. So this is what you are doing. So calculate this and replace this line with this. And what does it mean? For example, here, let me see. So you have 1 minus half of this. R2 minus half of R1. 1 minus half of 2 becomes 0. This is exactly why we did it, because we wanted to make it 0. Now let's look at this. 3 minus half of 1 becomes 2.5. 2 minus half of 1 becomes 1.5. 0 minus half of 1 becomes minus half. 1 minus half of 0 becomes 1. 0 minus half of 0 becomes 0. 360 minus half of 240 becomes 240. Am I correct? I might be wrong. There might be a mistake here. 360 minus 120. Yeah, that's correct.
You're correct.
Yes, that's correct. So here, now let's move on to the R3. Let me erase this, but you have this in the video, so you can look it up again. Let me erase it so you can understand better. So now let's go to the third. So you have R1, R2. Now let's go to the third row. You have R3. Always put the R3 itself without any alpha, without any weight. And now use R3 itself and the pivot row, R1, but with some alpha, plus alpha. Right? Alpha might be negative or positive. You want this to become 0. Either do it in your head or calculate it. For example, if I want to do it with my head, I said I want to make 2 to 0. So I should say 2 minus this 2. So alpha is minus 1. And alpha is minus 1, so R3 minus R2. If you want to write it down, you should say R3, 2 plus alpha, R1, which is 2 here. I want it to become 0. So alpha is minus 1 here. Therefore, now let's calculate it. 2 minus 2 becomes 0. 1 minus 1 becomes 0. 2 minus 1 becomes 1. 0 minus 1 becomes minus 1. 0 minus 0 becomes 0. 1 minus 0 becomes 1. 300 minus 240 becomes 60. That's it. Now let's go to the fourth row. You can do the same. I want minus 6 to become 0 using 2. So minus 6 plus 3 times 2 becomes 0. Therefore, R4 plus 3R1. I want it to become 0. It's minus 6 plus 3 times 2 becomes 0. Minus 5 plus 3 times 1 becomes minus 2. Again, the same for everyone. So you have these elementary row calculations in order to, in this pivot row that you had, you want that pivot value to become 1 and all of the other ones become 0. And why do you do that? Because whenever you do that, you in the Tableau method, you always want to find the variables where it has only one value and all the rest as 0. And this variable will be called basic variable. We will introduce that in a few slides. So basic variables are the variables which have only one and the rest 0. This will be called basic variable in Simplex method, in Tableau method. And the other one will be non-basic variables. And you will see that at the end, when you have at the last iteration, when you have the basic variables will have non-zero solutions values as the optimum solution, but the rest will be 0. And we will see that. So this is the reason why we do that. But again, they will introduce the reasoning in more detail. Another thing that you should also note that whenever you are doing this, so you calculate the pivot column and pivot row, you replace this S. So it has some label, right? You replace the label of pivot row by the label of pivot column. So here, as you see, I replaced S1 with X1 because the label of this pivot column was X1. So this is also an important thing which you shouldn't forget. Now, continuing the table, we'll do the same. We continue until, okay, and we continue this procedure that I told you until all values in the 0 or the row of cost become non-negative, either positive or 0. This is what we do for Tableau method. So we continue that. I think this is the repeat of what we had in the previous slide. So this is, now let's continue that again. I'm repeating this here. I'm repeating it here. Now I want to continue it here in this table. Again, I do the same. I take among these, I take the most negative value, which is -2. This gives me the pivot column. Now I do the mean test. 120 divided by half, 240 divided by 2.5, 60 divided by 0, I ignore it. Among these two that I didn't ignore, which is the smallest one, this. So this will be the pivot value using elementary row calculations. What do? I say, okay, now I have this. So I want this pivot value to become 1, and the rest become 0. What do I do now? For example, for this, I have R1 and R2. R2 is the pivot row. So R1 plus alpha R2 should become 0, and I see that this is -1/5. You can calculate that all of them. So here you only have R2, so alpha R2 should become 1. So alpha times 2.5 should become 1. Therefore, this is dividing by 2.5. So you can do the same for all rows, and you will come up with this. And all of them are non-negative now. So you can't get the most negative value in the 0, right? Now, this is the end of simplex algorithm. And as you see, in each iteration that I said, pick the most negative one and choose this, we are moving from one extreme point to another extreme point. So that's why I'm saying that the Tableau method is an implementation for the simplex algorithm. It might have some other implementations too. The simplex algorithm is not just this Tableau method. Tableau method is just one of the implementations for the simplex algorithm. And by each of these iterations of the Tableau method, you are moving from one extreme point to another extreme point. And as you see, you are improving your cost function exactly as simplex algorithm intended to. For example, here, let me go to the problem. This problem, it was maximizing, right? Here, we started from here. We were maximizing this cost restrict with these constraints, which we converted the problem to this by adding slack variables. We were maximizing it. Therefore, we want to increase the cost. So starting from initially it started with the cost value was 0, right? Now let's go to the next slide. Again, next slide. 0 became 720. It improved. It increased the cost. The cost increased from 720 here. It improved to 912. So it improved again. It was increased. And we can't continue because we are at the end. We are at the best extreme point, and this is the maximum cost function. This is the C star. When we usually say a star, it means that the optimum, right? This is the cost which is optimum. And you can see 912 is the actual maximum of that function conditioned on those constraints. Okay. Once the table is over, the row having, by the way, when I did all of these, again, I replaced S2 with X2 here. As I said, don't forget that. And now you can see that here, sorry about that, each column, having only one, and the rest 0 is the basic variable. Okay, this is a basic. So these are basic variables. X1, X2, S3. As you see, because we replaced the label of the rows, pivot rows with the label of pivot columns, they are repeated here too, X1, X2, S3. These are called basic variables. The rest of the variables, which are X3, S1, and S2, are non-basic variables. These are terminologies in Tableau method, in the Simplex algorithm, right? And what does it mean at the last iteration here? So it means that X1 star, which is the optimum, is this exactly, 72. X2 star, which is a basic variable here, is 96. This is S3. S3 star is here. Sorry, 60. And this is C star. C star. 912. These are the optimum things. What are the rest? The X3 star, which is a non-basic variable, is 0. S1 star, the first slack variable, its optimum is 0. S2 star is also 0 at the optimum. Do you get it? So now we will see that why is we can check that whether our solution is correct or not. We'll see. So as I said, this is the optimal cost, 912, that we talked about, and these are what I wrote down, and the rest are non-basic, are 0. Now let's check whether it was correct or no. Do you remember this was the cost, the previous slides that we started, the optimization problem that we started from. And C star should have all of these variables as X star, right? Because we are at the end, we're at the optimal thing. So 6 X1 star, 5 X2 star, plus 4 X3 star. And what was X1 star that we found? 72. What was X2 star? Was 96. What was X3 star? Which was 0, because X3 was a non-basic variable. So if you calculate this, it becomes 912. Exactly what we had found for C star here. Correct. Correct. So we can check whether we solved it correctly or not. Did you understand it? Is it clear so far? Okay, great. Now, big M method. This is also something in the Tableau method. So we should use big M method when we have mixed constraints, when we have these constraints or equality constraints. Do you remember in the previous slides, I said assume that constants are all less than or equal to. Now assume that we have a maximization problem for now again, and the constants, some of them are greater than or equal to, okay? So we have mixed constraints. Now let's assume for now we have mixed constraints of greater than or equal to and less than or equal to, okay? Like this. So these constraints are less than or equal to, and this is greater than or equal to, and this is the default constraint that we have in standard problems, okay? And by the way, in the Tableau method, we always are assuming this, right? I didn't include these in the table because I was assuming that this is a standard problem. So for less than or equal to constraints, we use slack variables as we talked before. Again, for this, we convert them to equality, and the slack variables should be non-negative. So here, we are saying that maximize these. Oh, by the way, before that, For greater than or equal to constraints, now what should we do? We can't use slack variables. Why? Can't use. Because assume I add this slack variable, then it means that the slack variable should be negative. Less than or equal to 0. Should be non-positive. Therefore, but we said that the slack variables should be non-negative. I want the slack variables to be greater than or equal to 0. Why? Because if you remember, I added the slack variables as additional variables to the optimization problem, and by default we assume the optimization problems are non-negative. Do you remember? So, for example, in that problem that we had in previous slides, we had 3 x variables. We added 3 slack variables for 3 constraints, inequality constraints. So in total, we had 6 variables where all of them were in the first orthant, whereas all of them were non-negative. So the variables that we are adding should be non-negative in order to satisfy the standard form of the linear programming. Therefore, we can't do that. This doesn't work for us. So for greater than or equal to constraints, we use excess variables E and artificial variables A. A for artificial variables, E for excess variables. So we use 2 variables rather than 1 variable. And we do some trick. So we can, for this, we can convert it to equality again by this. We say by plus some variable minus another variable. And then we can assume these 2 variables are non-negative, but with different values, right? With different values, we can make it in a way that although these 2 variables are greater than or equal to 0, but this might be negative. Therefore, this might be satisfied. So this is a trick. We use 2 variables, each of which is non-negative, but we still can have equality, convert these inequality constraints to equality constraints, and we still are standard form of linear programming. But the additional variables that we have, we want them to be very small. Why? Because again, this is like what we had here. We want it to be negative, right? So this additional variable that I'm using for the trick, I want it to be small as possible. I don't want to be large. If it's large, then this equality might not mean necessarily the greater than or equal to inequality. For that, I want the additional additional variable denoted by A to be very small. Therefore, another trick I do in the cost function, which I'm maximizing, I add minus m a4. Here, capital M is a scalar. Although initially I said I usually denote scalars by small cases, but here, because of the standard notation of big M method, I have to put it a capital M. But it's a scalar. So a scalar, but a big scalar. It's very big, a big number. If it's a big number, then A must be a small number. So their multiplication is a small number, and I want to maximize this cost function, right? So I want to maximize this, but if I want to add this to the cost function and I want to maximize the whole thing, this should be very small. Do you agree with me? So assume this is not a small, this is very big. This is 1 million. So we will have minus 1 million. Whatever we have here, minus 1 million. This is very bad for maximization. I want the value of this cost to be maximized, but I'm also having minus 1 million. It's very bad. It's awful. I want it to be minus 0.0001. I want it to be very small, so negligible compared to this. Therefore, I can maximize that. So I'm saying that by this, I'm forcing A to be small. Otherwise, this will blow the cost function in a way that it will be awful for the cost to be maximized. Note that this is negative. This is not positive. This is not plus MA. This is minus MA. So this is minus. If it was plus MA, then A would be large, because it says I want to maximize this. Then let MA be very big, so it maximizes the cost However, I'm maximizing this with minus. It means that M is large, therefore I have to make A very small. So it's intrinsically or implicitly, I can say, implicitly making A very small by setting M to be very big. So far clear? Yes? Okay. Now, so I add this to the cost. I also had these slack variables for the less than or equal to constraints. For the greater than or equal to constraint, I have these additional and excess, and all of them are non-negative. Again, the default constraint in the standard linear programming, and we have these, all of these as objective variables now. Okay, let's form the table for that. Again, I put all of these with the order that I choose, but I stick to the order until the end. I put the slack variables and the additional variables, all of them here. I don't put the excess variable here. Okay, and then I write the constraints here. Again, as I explained, the first constraint is this, the second is this, the third is this, and the fourth is this. So in the fourth, for example, we have 1x1, 2x2, plus 0s1 plus 0s2 plus 0s3 plus 1a4 minus 1e4 equals 150. And this is the cost row minus 3. Again, I write it in this way. I bring it to the left-hand side. Right? So see, minus 3, x1 minus 4, x2, plus all of these 3, 0s3, 0s2, 0s3, plus, here it becomes plus because I have brought it to the left-hand side, plus ma4, plus 0e4 in the cost, and something. It's 0, okay? It's 0 here. Now, I want this additional variable to become a basic variable. Therefore, I try to make this 0, so I only have 1. So always when you have additional variable, you should do this. You should try, before continuing the table, try to make the additional, the column of the additional variable a basic variable. Therefore, you will have 1 and you want to make it 0. For that, you have R1, R2, R3, R4, R5, right? So you will have R5, and you only have this row because all of these other are 0. You can't use them. You only have R4, where you have 1 for A4. So using R5 and R4, you want to make it 0, like what we had before. R5 plus alpha R4. Here, M plus alpha times 1 should become 0. Alpha will be minus M. Right? So this will be minus 3 minus M times 1 becomes here, minus 3 minus M. Minus 4, minus 2, minus M times 2 is minus 2M minus 4. 0, 0, 0. So here, M minus M times 1 becomes 0. 0 minus M times minus 1 becomes M. 0 minus M times 150 becomes minus 150M. Okay, so this is the only difference compared to the previous example that we had. Now, if there is any question, please ask me. Okay, you should understand the procedure. Now, again, as before, let's choose in the 0, let's choose the most negative value. What is the most negative value? Here, consider M as a big number. Do you think minus 3 minus M is most negative, or minus 2M minus 4, or M, or minus 150M? Sorry, you don't consider this among this. You should only consider among this. M is positive, so this is not negative even. Among these two, which is more negative? This is smaller, right? So you choose this. This will be your pivot row, pivot column, sorry, pivot column. Now, do the mean test in the procedure. Do you remember? 600 divided by 1. 225 divided by 1. 1000 divided by 4, 150 divided by 2, and take the minimum among these. This gives you the pivot row. Now replace the label of pivot row with the label of pivot column and repeat the table. So here we'll have this. Now repeat the column. Now you want to, in this pivot column, you want to make x2 a basic variable in this iteration. Therefore, you want these to be 0, all of these, except this to become 1. You want to make it a basic variable. How? Again, using elementary row calculations that we talked about. So for example, here we are R1, and we can use R1 and R4, which is the pivot row. R1 plus alpha R4 should become 0. You can find the alpha. So you can have all of these. Also for this, let's talk about this. So this is R4, R5, R6. I don't care about R4 anymore, I5 anymore, because I replaced this C row with this in the previous slide. Now, so I have R6 and R4. So what should we do? We have, for example, -3 minus m. This should become, so here, -2m minus 4 this should become 0, and this should become using this. So R6, let me write it here. R6 plus alpha R4. What is R6? -2m minus 4 here. Plus alpha, what is R4? 2. This should become 0, yeah? Yes. I want to make everything 0 except this. So what is alpha? 2 alpha becomes 2m plus 4. Alpha becomes m plus 2. Therefore, I will have R6 plus m plus 2 times R4. And if you calculate this, for example, here, -3 minus m plus 2 times 1, it will give you -1. -2m minus 4 plus m plus 2 times 2 gives you 0. 0, these are 0, 0, 0. Why? Because 0 times plus m plus 2 times 0 becomes 0. 0 plus m times 2 times 1 gives you m plus 2. The same for everyone. Also here, minus 150 m plus m plus 2 times 150 gives you 300. So far clear?
Yeah.
Okay, great. So now I repeat. Why do I repeat? Because I still have negative value here in the 0. I repeat, I get the most negative value. This is a positive. I get the most negative. This is pivot. This gives me pivot column. I do the mean test. Here, why do I ignore? Because this is a negative value. 75 divided by -half. I ignore that. Among these, I take the minimum. This gives me the pivot row, and do the same element row-wise elementary calculations, and then I will come up with this table, where in the 0 all of them are non-negative or positive here, non-negative. So this, as you see, let's go over the tables that we had. We were maximizing the cost function. This was minus 150 and a very negative number. Became 300. It's improved. 300 became 900. It's improved. We are maximizing. Again, we are moving from one extreme point to another extreme point in the simplex algorithm, right? And we stop here because this is the best extreme point that we have found. And these are the basic variables, which are here too. S1, as you see, all of them are 0 except here, S1. E4, you can see it here. All of them are 0 except here. S3 is a basic variable. All of them are 0 except here. X2 also here. I think this should be 1. Yes. All of them are 0 except here. So we have these basic variables, and I write it here, as you see. See, S1 star is, let me write it here so you can see, 375. Again, E4 star is 300. do this for until this. Now let's check the answer. C star is 3x1 star plus 4x2 star, because this was the cost function. Now I ignore m. Now because minus m a4 already becomes 0. Why? Because I already found a star to be a4 star to be 0. So that's why we added that part to the cost function in order to make a very small until a became 0. Now I only have this cost function. So 3x1 star x1 was a non-basic variable, which was 0, and 4x2 star for 200 times 225. It becomes 900, and this is exactly equal to this, correct. So using a trick, so additional variables and excess variables, as well as the big M method, we could handle greater than or equal to inequalities, right? Although still stay standard linear programming optimization problem, because all of our variables, objective variables, were non-negative, right? Okay, another example for mixed constraints. Consider another. So here we have this, we are maximizing, we have 3 variables. Now we have equality. In the previous example, we didn't have equality, right? We have less than or equal to, which is simple to handle. We have greater than or equal to, we need additional and excess for that. And what is, now we see how to handle equality. We also have this default thing for the standard linear programming problem. And there is also another thing that I want to let you know in this example. Assume you have a DC, a bias. In electrical and engineering words, you can look at it as a DC signal, so, or a bias, a constant added to the cost function. That's why I call it DC value or bias value, doesn't matter. If you have this, drop it for now, but don't forget to add it back at the end. So convert this cost to this. This DC might be negative or positive. It must be not negative 4 or positive 4. Doesn't matter, plus 4. Drop it for now, but add it at the end. Why? Because so whatever function you have, like this, so you are minimizing it or maximizing it. It's another function, you can see it as a maximization problem. If you remove the DC, it becomes like this. You will calculate this. The arg mean will be the same, but the mean will, you need to add the DC back to get this mean. So the arg, your arg mean or arg max will be the same, but you need to add back that DC or the bias that you removed in order to retrieve the optimal solution for the actual cost function that you had before dropping. Okay, now for, is it clear the bias that I discussed? The bias that I talked about, right? Okay, for the inequality constraint, we add the slack variable. For the greater than or equal to inequality constraint, we add the additional and excess variable. For the equality constraint, we also add additional constraint. There's no need for excess variable. We add the additional variable. And you will see that this additional obviously should become 0 at the end, because x2, this was already equality. What we need to handle this, why? Because we need to have something, some row for this constraint in the table. If you don't have any variable in this constraint, then how do you involve it, include it in the table? So therefore, we add some variable, additional variable to this constraint, although it's equality, but we know that its optimal will be 0 at the end. And these again should be non-negative, right? So let's solve it. Again, we have 2 additional variables. Do you remember? One for here and one for here. We can multiply both of them by m, a big M. Why? Because we want this to tend to 0. M is big. It forces both A1 and A2 to tend to 0. And we write the constants like this, and this is the default thing, right? Now let's write a table. So the variables, and here we'll have slack variables as well as additional variables. So we write them here with some order, and we stick to the order until the end. So here the first constraint, 1x1 plus x2, and all of this, you know how to complete the table, as I told you before. Now we have this row, so minus, do you remember? So see, I bring all of these to the left hand side. See, minus x1 minus plus x2 minus 3x3 plus ma1 plus ma2 equals 0. So I write it here as I have written it here. Now I want, now these two are bothering me because I want, as I said, for additional variables, try to make them basic initially. For here, I want this to become 0 and every except here. And for this, I want this to become 0 except here. Both of them, I want them to become basic variables. For now, first, let's talk about A1. I want this to become 0. How? I have, so this is R1, R2, R3, R4. I have R for this. I'm talking about this now. R4, I have only R4 and R2 because these are 0. I can't do anything about them for using them. Whatever you multiply by 0 becomes 0. You can't do anything. So you have R4 and R2. How do I make it 0? I can say R4 minus MR2. So this M minus M times 1 becomes 0. So now I do this for all of these. So here I say minus 1 minus M times 1 becomes minus M minus 1. 1, sorry, here. 1 minus M times 0 becomes 1. Minus 3 minus M times 1 becomes this. And so on and so forth, right? So we can have. And again, we still have here. Now let's work for the A2. I want to make it basic. Here, this is R5. This is R6. Now, in the R6, I want to make it 0. How do I do that? I say R5 minus M R5 here that we are now. And we also have here R3 only because the rest are 0. I can't do anything about them. So R5 minus M R3. If you do the elementary row-wise calculation that I said, you will come up with this row. So your row, cost row will be this. You will use this. And these are the rest of the rows that you have. Okay. Now, now that you have made the columns of the two additional variables, basic variables, now let's choose the most negative value in the row, in the cost row. What is it among these? What is it? Minus M minus 1, minus M plus 1. Of course, this is more negative than this. Minus 2M minus 3, and M is positive. So this is the most negative one. So this is the pivot column. And now you have the pivot column. Let's do the mean test. So 220 divided by 3, ignore it. By 0, ignore it. 5 divided by 1, 5. 10 divided by 1, 10. This is smaller. So you take this. This is a pivot row. Do the elementary row-wise calculations that we talked about, and you will get this. You will get this table that we talked about. Again, sorry, wait, yes. You will get this, and I have replaced the label of this with this. See, X3. I do the elementary row-wise calculations. Again, as we discussed before. Why? Because we can't stop. We still have negative values in the cost row. I do the most negative. I choose the most negative value in the cost row, and I do the same mean test. Again, I choose the pivot row and do the elementary row-wise calculations, and I come up with this. Again, for these are the pivot rows and pivot columns in this step. So in the next thing, I should replace A2 by X2, right? I have done that in the next slide. See here, I have replaced A2 with X2 as we discussed. And we finally come up with this table where all of the values in the cost row are non-negative, because M is a big number, M minus 1 is a big positive number, M minus 1 is, of course, non-negative. And these are also non-negative. It can be 0, non-negative, 0 or positive. Therefore, we are done. We are at the best extreme point in the simplex algorithm, right? So these are the basic variables. You can find them here too. You can find them here, here, and here. You can find them here too, right? So you write these, and also C star is 10. You can also check, as we discussed before, correct. Now, don't forget to add the DC back. You need to, these are the actual arg means or arg max. These are correct, but this is not the actual maximum cost function. You need to add the DC or the bias back. For that, you had 10, you had plus 4. If you had minus 4, you had to add minus 4. So 10 plus 4, 14. This is the actual maximum cost function. So far clear? Is there any question? Can you please give me any feedback?
Yeah, clear. It's good.
Okay, good. By the way, as you see, it's a simplex algorithm, and the Tableau method is just a procedure. But great. But we will see that in the later sessions when we are done with a simplex algorithm and linear programming. We'll see more interesting algorithms. I think they will be less procedure-wise, the algorithms, but this is like a procedure. You need to know the steps and to do them correctly. So, okay, and now the reasoning. So you might say, why we are doing this? Now let's talk about reasoning, and I think the session will be over, but the reasoning is important. So assume that we have this maximization problem, okay? We convert this to this using slack variables. So you can see, yeah, the slack variables, and this is what we have for the default thing. The number of variables is 7, number of equations is 3. Okay, so we can have 4 variables to 0, because of course 3 of them will be basic variables, so equal to the number of constraints will have basic variables, right, which will be non-zero values. They might be 0, but they might be non-zero, but the non-basic variables will be definitely 0. So we might have 7 minus 3. We have 7 variables in total, minus 3, which are basic variables. We'll have 4 non-basic variables, which will be 0. So we need to find the 3 variables which are basic variables, right? And you can choose, it's a choose 3 out of 7. So we have 35 cases for choosing different basic variables out of these 7 variables. But let's go, for example, one by one, see some examples. One of the ways is this. For example, assume that the non-basic variables are these: x1, x2, x3, x4, all of the actual variables that we cared about in the initial problem. Let them be non-basic variables 0, and we find the slack variables that we added, and we consider them as basic variables. Maybe the basic variables are only the slack variables, right? One of these 35 cases is this. So the cost will be 0. Why? Because the cost was this. The cost will be 0. And if you put x1, x2, x3, 0 in these constraints, you will get this. S1 equals 50, S2 equals 42, S3 equals 250. And again, they are non-negative, of course. Therefore, this is the solution. Then the cost is 0. Okay. Now let's look at another way that we can choose the 3 out of 7 basic variables. So assume I take x1, x4, s1, and s2 as 0, and the other 3 as the basic variables. So x2, x3, and s3, for example. This is one of the 35 cases. So if you put these values to 0 in the optimization problem that we had here in this slide, here, you will get this. You will get this. And you can easily solve it. How? x2 equals 42 divided by 3. Now put it here. You will get x3. Now you put x3 here. You will get s3. And you will check that all of them are non-negative. So you will get these numbers. And the cost, you put x2 star in the cost, and you will get 84. Now compare this 84 to the previous one, which was 0. Of course, we are maximizing, right? We are maximizing. Of course, 84 is better than 0. Therefore, this solution in this slide is better than the previous solution, than this solution, right? So we can calculate all the 35 cases and see which one is better in terms of maximization. And we will say, okay, those are the 3 basic variables and the other are non-basic variables. We can do that. But we want to do it in a wise way. We don't want to check all of the cases, because the more variables we have, the more headache we'll have. We'll have more number of cases. Which variable should we increase, which maximizes the cost function the most, right? Assume this was the cost function, right? What is the wise way to find the basic variables is that let the basic variables be the variables where we want to increase when we increase that variable, the cost functions increases the most. Why? Because we want to maximize the cost function. And in this cost function, you tell me which one among x1. So slack variables, when you increase the slack variables, the cost doesn't change here in this example. But if among x1, x2, and x4, if you increase them, each of them, which one has more effect on increasing C? Can someone answer me? Hello? Can some?
Well, x2 would have the greatest effect.
Exactly. Because its factor is positive and is the most positive number. It's greater than 4. So whatever you increase, 6 times 6 will have more effect than times 4. -5 is even worse. When you increase x4, it will decrease the cost function. So among all of these, x2 is better because it has the biggest multiplication factor, which is positive. And recall that we had this. Do you remember? We brought all of these to the left-hand side. Therefore, this. That is why do you remember in the Tableau method, in the first step of each iteration, we take the most negative value in the cost function row, in the 0 cost row. Do you remember? And that's why. Why do we get most negative? Because before moving it to the left-hand side, it was like this. So actually it had the most positive multiplication factor. When we brought it to the left-hand side, that factor has become the most negative multiplication factor. That's why when you are choosing the pivot column, you are choosing the most negative value in the cost row. You are actually choosing x2. You're saying that I want to take care of x2 because I know that increasing x2 will have most effect on increasing the cost. So that's why the most negative, because you brought it to the left-hand side for pivot column. So that was the reasoning for pivot column. Now, what is the reasoning for mean test? For mean test, you have this. So I think we don't have enough. Maybe let me tell you this and then we will conclude the session. So how much do we, so here we chose this -6, which was the most negative one. And now here, you tell me in the first constraint, the worst case scenario in the first constraint here. The worst case scenario is that x1 equals x3 equals s1 0, and the most we can increase is x2, right? Because we chose x2 as a pivot column, and if we set these to 0, they can't be negative because of this constraint, default constraint. The worst case scenario is that we set the other one to 0 and x2 will be 50, right? In the second constraint, what is the worst case scenario? So we set x1, x4, and s2 to 0 because they can't be negative. So 3x2 will be 42, right? Otherwise, x2, in other words, x2 will be 42 divided by 3. Here, in the worst case scenario, you set x4 and s3 to 0, x4 and s3, all of them to 0 except x2, but you don't have x2, so you will have nothing, 0 x2, nothing x2 equals 250. Therefore, alpha should be infinite. So in other words, when you set these to 0, because you don't have x2 in this constraint, your x2 will become infinite. You don't have that. Therefore, this is exactly what we are doing here. These are the calculations of mean test. See, here in the worst case scenario, I'm putting all of them to 0, and I'm getting 50 divided by 1. Here, I have it. Here, I'm setting all of other ones to 0. I'm getting 42 divided by 3. So I'm finding out what is the most value that I can increase x2, which I chose in the pivot column. What is the most value that I increase that pivot, that variable, to have the most increase in the cost function, in the objective function. This is what we are doing in the mean test. And why do we do the minimum of them? Because we can't increase, so x2, the most that we can increase is either 50 or 42 or infinite. We should choose the lower bound between them. When we say that here we say that we can't increase more than 42. Here we say that we can't increase more than 50. Here we say that we can't increase more than infinite. Among these, I should take the minimum. I can't increase more than 42. That's why we do the mean test. We take the minimum. I think the reasoning now for mean test for the pivot row, pivot column, and pivot row, choosing the pivot row now is obvious to you. Is it obvious? Is it any question?
Yeah, no, it makes sense.
Okay, great. As I said it very fast because we ran out of time. Maybe I will review this reasoning with more, with less space next session, and then we will continue that. But before that, before we conclude the session and I ask for your questions, is that very soon I will upload your assignment, and I will have some time. I'll give you enough time to solve it. And the first assignment will include the maybe one or two questions from the preliminaries, and also some questions about linear programming Tableau method. You will solve that, and also you will have one programming question where you implement this procedure that we discussed today using Python language. I think it will be a for loop. You get it, right? We will have a for loop over these iterations, and in each for loop, you take the biggest negative value in the cost row, and then you will take the pivot column. You will do the mean test. So it's a procedure in the for loop until in the while loop. In the while loop, your termination condition will be when all of the values in the 0 are non-negative, and then you will return the value. You will also check whether your answer is correct or not, as we checked here, and this will be, I think, an interesting thing that you can implement and enjoy. So yeah, I will try to post it as soon as I can. I'm preparing it. It's not yet finished, but I will do it as soon as I can, and you will have enough time to submit it. I will also make a Dropbox in the course link, so you can upload your questions in the folder before the deadline. Okay, great. Is there any question?
When is it due?
When is it due? Just give me a second. Yeah, I think. So if you agree, the due will be February 10th or a bit more. I'll set it. Is it fine with you guys?
Yeah, that's fine with me. How many assignments
Yes.
do we have though? Because isn't that, will we have enough time to do all the assignments? If
There will be 3 assignments, but there will not be large assignments. So they will be small assignments, but 3 assignments. And I think the reason that yeah, I'll try to make it a bit more. Someone said in the chat, more please. But I need to give the TA time to also grade your assignments. And I also have told him not to take very hard on you. So as I said in the initial sessions too, I'm not going to take hard on you guys. So you don't need to worry about that. But please try to answer completely in a way that you get the most that you can. Okay, sure. But yeah, the reason that my restriction is also on the TA side too. So I need to give him some time to grade your assignments to that. Otherwise, I would give more time for the deadline. I would try my best to give as much as I can for the deadline in a way that also TA can grade them. Someone said, ask any question about the assignments. Did I answer it? Or yeah, the assignments, you said how big they are. They are not very big. I think they are not very small. They are not very big. They are, I think, average size. Is there any question? By the way, one other thing that I wanted to tell you, one of you guys also emailed me regarding that, is that your midterm, I've decided to put it after the reading week, so you have time to read for that, more time to read for that. So it will be on the 8th week, and I think it will be around February 28th. It will be after the reading week. Is that fine? Is that fine with everyone?
so it'll be the week of February 28th or on the 28th?
On the 28th, which will be the week of the 28th, right? So because the week of February 19th to February 25th is the week of reading week. Yeah, I think you will have time, freedom to read. Also, for the assignment 2, which part of it will be on that time, I will give you more time for your assignments to solve, because I know that you're also studying for your midterm. So I'm completely understand that. I don't pressure you for that. So I will give you more time for assignment 2 in order to have time to also read for your midterm. And I will try my best not to take very hard on you. Don't worry about that. Is everything fine?
The 28th is good with me.
28th, right? 28th.
Yep.
Yeah. And please check your calendar. You will see that I think February 20th to 25th is the reading week, and in that week you don't have a class. Yes. Someone asked
Hi, Ben.
to.
So I actually wanted to know that the timing for the midterm exam would be this time in the class timing, or would it be in the morning?
I also thought about that, because if we put it in the morning, some people might have some conflicting class or some conflicting schedule and other time. So we can't do that. Yeah, that's
why I
why.
have also another exam on the 28th that morning,
Yeah.
I think.
Oh, I apologize for that, but
That's no problem.
Okay, but no, it will be on your class time, and I think I will. We will be in the class. One thing that I can say that it's better for you guys to have a computer which you can turn on your cameras, but I will trust you. I'll trust you. If someone doesn't have the equipped for that, for camera or that's in that or that thing, I will understand that. But try your best to have a device which has a camera. But apart from that, I will trust you. I don't use the softwares which check your browser or something. I don't do that because I have trust in you. And if two solutions are exactly the same, and then that can be considered as cheating. But I'm not a cheater seeker, or some people might seek for catching cheating and these things. I'm not that kind of guy. You don't need to worry about that, but try not to cheat, and I trust you guys. And I don't expect any two solutions to be exactly, I mean, or the whole exam to be exactly the same. It means that they have cheated, obviously. Yeah, but I trust you guys. And just try to have a device. I appreciate that if you do that, which you can turn on one camera. And I will be in the class. In the class time, you will have the exam, and you will have time, and you can ask your questions during the class. It's like we are in the classroom, and you are taking the test, and if you have any ambiguity or something, you can ask, and everyone can hear my answer to your questions. Is it good?
Sounds good.
Sounds good. Okay, great. Yeah, and I think this, and for the assignments, as I said, I will try my best to do it as soon as I can. What exact time of the exam? Yeah, I think that the exam day, the time will be the class time. So no one, it doesn't conflict with anyone's schedule. I respect your schedule. I don't want it to be conflicting with your schedule. Yes. Okay. Any other question? Great. Okay, so please expect from me, check your course link. Soon I will post your assignment as soon as I can. When I haven't done that, it means that I'm still working on it. It's not meaning that I don't want to put it. I'm working on it, and I will try my best to put it as soon as I can, and I'll give you time. Is that good? Great. Okay, thank you very much. Thank you, everyone. Sorry for we went over the time for a few minutes. Thank you very much.
Thank you.
Thank you.
Thank you. Have a good night. Thank you.
Yes. Good night.
Someone asked a question? No?